Assalamualaikum and greetings to all. Today's topic is on applications of partial derivative. The first application of partial derivative is increment and differential. Okay, let z equals f of xy. So here, if x increases by delta x and y increases by delta y, then z will increase by delta z. So where the increment of z, which is delta z, equal to f of x plus delta x, y plus delta y minus f of xy. Okay, so now from the definition of partial derivative on the second page, this is the definition of partial derivative, where partial f partial x is equal to limit of this as delta x goes to 0, and partial f partial y is limit of this as delta y goes to 0. Now if we drop the limit, if we drop the limit, then we get approximately equal. So partial f partial x is approximately equal to this, and partial f partial y is approximately equal to that. Okay, which implies that if we use the first equation here, if we do some mathematical manipulation, f of x plus delta xy minus f of xy is equal to, you do the cross multiplication, is equal to partial f partial x times delta x. And using the second approximation here, f of xy plus delta y minus f of xy is equal to partial f partial y delta y, this one. Okay, now instead of taking this, if we take delta z equal to, we put delta x to x, take the difference, and then f of xy plus delta y minus f of xy, then we can see that the expression in the first square bracket here is partial f partial x delta x, and the expression inside the second bracket is equal to partial f partial y delta y. So from here we get delta z is approximately equal to partial f partial x delta x plus partial f partial y delta y. Okay, now we go to the definition. Okay, so the definition says, suppose z equals f of xy and partial f partial x and partial f partial y exists, meaning that the partial derivative of the function exists, and if delta x and delta y are increments of x and y respectively, then an approximate increment delta z of z is given by this. So this is very important, you need to remember this. Okay, so if x and y have increments, delta x and delta y, then the approximate increment of z given by delta z is equal to this equation. Okay, so as you can see, we use partial derivative in the formula. All right, now if delta x goes to 0, very small, very close to 0, delta y is very small, approaching 0, then the increment in delta x is denoted by dx, increment in delta y is denoted as dy, and increment of delta z is denoted by as dz, and dz is known as the differential of z. So delta z is approximately equal to dz, and the total differential df of f is given by this. As you can see, you just change delta to d. Okay, the formula is similar. Excuse me. And of course, we can extend this to function with 3 independent variables. So for 3 independent variables, we have 3 terms. So this is the increment in w, and this is the total differential of f. So you can see they're very similar, but instead of delta, we use d. Excuse me. And as you can see in the 2 equations here, this one and that one, we use partial derivative. Okay, partial derivative. So this one is the increment in w. This is total differential of f, or total differential of w. Here we have 3 independent variables, and in the first definition here we have 2 independent variables. Okay, so the total differential and the increment here can be used to find approximation. Right now, let's look at an example. Okay, so here, in the first example, we're given z equals 3x squared minus xy. Use a total differential to approximate the change in f as xy varies from 0.12 to 0.1, 0.01, 1.98. Okay, so here we have 2 independent variables. Example, z is equal to 3x squared minus xy. Okay, and it says use total differential. So for total differential or increment, you can either use this formula or that formula. Oh, sorry, two independent variables. So this one, oops, you can use the approximation increment in delta z, this one, okay, on page 14. All right, so we're going to use this formula. So you can, for approximation, you can use increment, the formula for increment, or the formula for total differential. Okay, so back to our example. Right, so here the point, so xy is supposed to be 1, 2, but then it changes to 1.01, 1.98. So here you can see that there are changes in x and also changes in y. Okay, we want to know what happened, or what are the changes in z, or in f. All right, so let's find the changes in x, delta z. So delta z would be the changes in z. So what you do is you take the new value minus the old value. So from here you can see that there is increment in x by 0.01, and the changes in z, in y, is 1.98 minus 2. So here is negative. So for y, it sort of decreased by 0.02. Okay, so for x it increases by 0.01, and for y it decreases by 0.02. So we want to know what happened to z, the approximate change in z. So from the formula, the approximate change in z is equal to partial f partial x delta x plus partial f partial y delta y. And we already calculated the delta x and delta y. So we need partial f partial x and partial f partial y. Oops. Okay, so this is equal to, all right, let's get the first term. Partial f partial x, differentiate f. So here we have our f with respect to x. So first term we have 3x squared, so that will give us 6x minus y. Okay, we need to multiply that with delta x, and the second term, partial f partial y, differentiate f with respect to y, we get 0 here, and we get minus x. So I'm gonna okay, minus x and delta y. Okay, just using the formula. And the next step is to replace delta x with 0.01, delta y with negative 0.02, x with 1, and y with 2. So this is approximately equal to 6 times 1, and y is 2, times delta x, which is 0.01, minus x, x is 1, delta y is negative 0.02. So from here we get, that's a 4, so 0.04 plus 0.02, which is approximately equal to 0.06. So that would be the approximate change in z when x increases by 0.01 and y decreases by 0.02. so we use partial derivative, total differential, to calculate approximate change in z. Okay, now we can also extend this to function with 3 independent variables. Okay, so for 3 independent variables, are we going with time? Okay, yes, we can solve one more example. The next example, it says let the measurements of a cuboid vary from 9 cm, 6 cm, and 4 cm to 9.02, 5.97, and 4.01 centimeter. Use the total differential to approximate the change in volume. Okay, so here the function is not given. Unlike the first example, the function is given, but the function that we're looking for is just volume of a cuboid. So everybody knows how to find volume of a cuboid. So let's say here we have a cuboid. Okay, I'm going to use x, y, and z here. Let's say this is x, y, and the height is z. And the volume of a cuboid, let's call it v, is equal to the width times the length times the height. Okay, let's say x is equal to 9 centimeter, y is 6 centimeter, and z is 4 centimeter. But now there are changes in the measurement. Instead of 9, 6, and 4, it sort of varies to 9.02, 5.97, and 4.01. So from there we can get delta x, delta y, and delta z. So delta x is 9.02, the new value minus the old value, so that would be 0.02. And for delta y, it's 5.97, so it sort of decreased by negative 0.03. And for delta z, it increases by 0.01. Okay, and our function is this is our function, volume. Okay, so these are the changes in x, y, and z, and we want to know the changes in the volume. Okay, so we want to know the approximate change in the volume. Okay, so we're going to use total differential, or the increment. Since this is a function with 3 independent variables, so we should have 3 terms. So we're going to use this one. Okay, we can use that one as well. It's sort of similar, total differential and increment, but I'm going to use this, okay, because we have the delta there. Okay, so the approximate change in the volume, so we want to find the approximate change in the volume. So the approximate change in the volume is delta v, so it's going to be approximately equal to, okay, so it's going to be partial v partial x delta x, partial v partial y delta y, plus partial v partial z delta z. Okay, or you can use f if you like. Alright, so for partial v partial x, differentiate v with respect to x, so that will give us yz times delta x. Second term, partial v partial y, that will give us xz delta y. And the third is xy delta z. Okay, now write down, replace x, y, and z with 9, 6, and 4. So here we have 6 times 4 times 0.02 delta x. And for x we have 9 and z is 4, and delta y is negative 0.03 plus xy, x is 9, y is 6, times delta z, which is 0.01. Okay, so that will give us, oh, I don't have my calculator with me. Alright, I'm just gonna let you find the the value here using your calculator. Okay, all right, and then I will continue with the next video about error. Okay, I have to use another video, otherwise it will be too long. All right, I hope you get the value here. All right, that's all for today. Thank you.